Hello, good folks. On the last video we talked about mappings and sets. So to quickly recap on mappings is basically you have what's called a domain and a range, and then a domain is basically it's also called the independent value, in which you have basically a set that's set of elements that you can apply to a given function, and that function would produce a result, and that set of results is called the range. Now, what differentiates a function from mapping is that functions should have basically two properties, or two properties should be sufficed. The first one is that every element in the domain has to have a range or a value. It points to a value, and it only points to a single value. It could be that multiple elements in a set point to the same value in Y. Say, for example, you have X and Y elements. So X, every element in X should point to an element in Y. However, if an element in X points to two elements in Y, then this is not a function, it's mere mapping. And all of these notations are basically saying just that. So we on the last video we also talked about. So I usually keep the notes here just to do like a quick, to be fast on the recap. And we know this, since my eye caught this function, we know this function is to retrieve the number of combinations for a given number of elements in a set. Anyway, so we know about all of this. We know the commutative and associative properties of the union, the intersection, and again, we know what this is, symmetric difference. And this is the abstraction of division, which is denoted by the symbol on the symbol there. This is called delta. And what we know is that this is basically an exclusive order. So you have both elements, the elements of both sets, but not the intersecting elements. All right. So what else have we talked about? So this is the domain and this is the range. Yeah, this is completely all right. So the other thing we talked about was the mapping. So I had this noted down because it just had different terminologies, different sources say the difference. So the thing was, there were some sources that differentiated between mapping and functions, and there were other sources that basically treated them the same. And the main difference that I came to conclude was, again, the function has two main properties that should be sufficed. If those would not suffice, anything else is just a mapping. And then what this means means that all functions are types of mapping, but not every mapping is a function. What else? Mapping any prescribed way of assigning to each element a particular set, the same set. Transform to do what mapping means, taking a set and applying a rule to it. Yeah, so basically these two definitions here mean everything. Is used so much that it has even a name. Locus, set of all points, usually means that the points make a continuous curve or surface. Okay, so we started to do a bit of exercises, and then we stopped at around where was it? So math police question. So we stopped at this symbol here. If you go back, if you just like go back, or if you just go back, like, I can't really go back. I don't think we can go back here. But anyways, we basically stopped here. So all the previous examples or the previous exercises, it was about, let me open up the video real quick. Today is another topic on, so this was the video. Let's fast forward to about, I think it was right about, and I can see that there are some graphs here. So this is basically what we've done. And then there were other questions on if in a graph and the line crosses multiple, what do you call it? If the line crosses multiple points, then you basically end up having a known function. It's a valid it's a valid mapping, but it won't be a function. Like in this case, C. In this case, you can have there's always one x but different values for y. So this is void. So this is not an actual function. And I think we should have noted this down because I think this is important. So let me write that down. Let's do x. If x has multiple y values, then that is not a function. In other words, the line has two intersecting points on the graph. That's it. So we can like go for the graphs. It would look nice
at two similar points.
So if you're going to see,
is related to more than.
There we are. So we could have the snipping tool. We just have this in the set of notes. It's not that clear, but it should suffice just fine. Then we should have that examples. And then we could also do
one value of y. C does not illustrate a function. Not a line crossing multiple points at the same time.
In this case,
it's definitely B.
There's another example here with B, which we should keep. Here we are. Example 2. And there we are. So that's basically like a super quick recap. And then we stopped at this notation here, which is J. There's a small circle, an F, and a hollow circle, F, and then X. So what this means is that it's a if you can see the title, it's composition of functions. So f of x, whatever f of x, you apply it to g of x, and f of x becomes the x for g of x. Confusing, and if I said it, I mean theoretically, let's see the details around here. So you have a function and then the g. So if you have g circle f of x, you start with the right hand side. So f of x applied to g of x. You can see it here. So f of x becomes like the x for g. Yeah, and this is a really nice illustration here on how he replaced the x with a placeholder called an input. So x is actually a placeholder, so you just replace the x with an input. So you have f of x in this case equals 2x plus 3. So 2x plus 3 becomes the x for gx. So in this case, you take the whole thing and put it in and replace x with the whole function. No, not a function. Yeah, the whole function here. And this is what you get g. I'm not sure what to call this, but let's call it composition with f. Yeah. And this is something quite interesting because you basically so you can have a function with an input that works for that function but doesn't work for the second function. So I think we get to know more about this down the line, if I'm not mistaken. I've read it somewhere, but yeah, I will explore it together. No worries. Anyway, so you have 2x plus 3, and then you apply 2x plus 3 to x squared, so it becomes all squared. There we go. So if we reverse, so association here doesn't work. So this is not really a property that you could that could result in the same. So if you reverse the order of g and f, you start off with gx, so we know that gx is x squared. So you apply x squared to x plus 3, so x will be replaced by x squared, so the value wouldn't be the same, right? And that's what, so you can see here that the term is rarely the same, because there are chances that you might get the same result if the functions basically were the same. But anyways, so let's not call it associative or commutative here, simply because the rule doesn't apply for all. Anyways, so the symbol is, it's not a field. The symbol for composition, is a small circle. It's not a field in dots, as that means a multiply. Yeah, so composition is a small circle. I thought it would have some sort of weird name like delta or whatever. But it's good that its composition is denoted by a small circle. We should have this in the notes. It's important to know. Not a dot. That means a multiplication, so you should watch out for that. So there's a function composed with itself, so if you compose this with itself, then you have like basically 2x plus 3, and then the x would be 2 multiplied by 2x plus 3, just like here. And then you apply the 2's, and then you have 4x plus, I don't know, 6, and then plus 3, you'll end up plus 9. So 4x plus 9. There we are. We should be able to do it without the pretty diagram, which is this one here. So yeah. Oh yeah, this is the domain. Yeah, this is what I was talking about earlier. Sometimes you have a domain that you apply to the given function, to the first function, that doesn't apply for the second function. The domain, so it's very important to consider the domains at all times. So to further illustrate on what I mean, let's explore this section here. So it has been easy so far, but now we must consider the domains of the functions. So we all know what the domain is and what the range is, and then we also know that a codomain is basically the set of y values that could exist, but not necessarily the range. The range is basically whatever is resulted from applying x to the function. So the domain of the square root of x, so we know we can't have a negative square root of a negative number unless we use imaginary numbers, but we're not doing that, so we must exclude negative numbers. So assuming the first function is a square root of x, where x belongs to all basically to all real numbers. No, unless it's 0 is included, so it's real numbers. Non-negative real numbers, so that's natural numbers. We know, if you go back to the list of notes, this is the very first topic we talked about. Positive natural numbers include the 0, and it's the same as non-negative numbers. So we could say that it's not natural numbers is a set of natural numbers. I mean, the square root is a set of natural numbers. And this is how they denote it by, and then x belongs to all real numbers such that x is greater than or equal to 0. Or we could use the interval notation. This is squared and squared brackets and curly brackets. No, curvy. It's important to get the domain right, which you could get bad results. And this is what I was talking about. We must get both domains right. Then the composed function and the first function used. So when doing, for example, G composition of F, the composition of G and F equals f of x supplied to G of x. Now, assuming that f of x is the square root of x, and then gx is x squared. Now, we should consider the set of elements here, the domains basically. So the domain for this one is non-negative real numbers. Okay, And in this case, for the x square, it could work for any number, so all the real numbers, actually. Now, x normally has the domain for all real numbers, so this is what you will end up with an x. But because it's a composed function, we must also consider f of x. So in this case, the domain changes. So in this case, when you're supplying in the first function takes on all non-negative real numbers. So, and then you supply all those non-real, non-negative real numbers to x squared. So you will end up with non-negative real numbers, which is the domain, the limited domain we started off with. So the domain is all non-negative real numbers. Now, so this is really important, and this is a nice example being used, assuming you have the composition of G and F, and then for the first function, the f of x basically uses, I don't know, for some reason uses metal only, and then the other one uses wood. So when you apply fire, it might burn it. So you'll only be using metal throughout the whole set. So wood wouldn't be used here because it was not supplied in early on. Nice. So that's that. And then what we could do next is so this is decomposing a function. We can go the other way and break up a function into a composition of other functions. The function can be made from these two functions. So we have f of x. Yeah, so it's basically what he's done is just try to create two functions. Okay, this could be useful. Decomposition could be useful if the function is complicated. I didn't know that could be possible. Some functions can be, but note that some functions can be decomposed into two or more simpler functions. Yeah, I think it would be easy if you have the set of domains that work with we've already went through this, the domains. Oh, this is quite interesting. I don't think we've covered all of this, but domains and the range. But I think we've covered most of it. I mean, yeah, I think we've covered most of it. We know that this is a codomain, but the elements resulting from x apply to the function is a range or an image. And range. What we put in, but we can define the domain. It's an essential part of the function. Change the domain and we have different function. Yeah, of course. Yeah. Yes, but in simpler mathematics we never notice this because the domain is assumed. Usually it's assumed to be something like all numbers that will work. Or if we're studying whole numbers, the domain is assumed to be whole numbers, and so on. But in more advanced work, we need to be more careful on the domain. The output, there are something different. What's the difference between codomains and ranges? Set values that actually do come out. We can define a function of f(x) equals 2x with a domain and codomain of integers. Thinking about it, the range is only even numbers, while the domain could be a set of integers. These integers are defined in that way, but the range is even integers. It's a subset of the codomain. We don't know the exact range because the function may be complicated or not fully known. square root of function. If we say the codomain is the set of real numbers, then square root is not a function. Is that a surprise? The reason is that there could be two answers for one input. F of 9 equals 3 or negative 3. A function must be single valued. Its codomain is correct, but it can be fixed by simply limiting the codomain to non-negative real numbers. So what we choose for the codomain can actually affect whether something is a function or not. Lots of word when few symbols will do. So there are ways of saying the domain is or the codomain is. The neatest way I know n says that the function f has a domain of n, the natural numbers, and a codomain of n also. And either of these say that the function f takes in x and returns x squared. There is also domain f, or dom f means the domain of function f. Range is that. Okay. So this is the domain, and this is the codomain, and this is the range. This is the codomain, this is the domain. Interesting. Let's do this copied to the list of notes. Nice. Now, yeah, we should do a set of exercises. So what I'll be doing now is that I'll be doing the exercises here and then moving to the composition functions and then finishing the mapping that we've done early on. So let me start off with the questions of the domain and the range. I think it's very important to have a full grasp of the so the function illustrated above, what's the domain? So we know the domain 2, 3, and 4 positive, so it could just be 2, 3, and 4. That's it. Yeah. Yep. That's it. That's the domain. For the function illustrated above, what's the codomain? 1, 4, 9, and 12. So simple. For the function illustrated above, what is the range? 4, 9. What is the domain for the function f of x equals 1 over the square root of x? So it has to be greater than 0, that's for sure. So x belongs to real numbers where x is greater than 0. Yeah, not equal to. Doesn't make sense. What is the range of the function f of x? The square root of x minus 2. So the square root of x minus 2. You really can't have to the square root, in this case minus 2, would equal to 0. That doesn't matter. But if it is the square root of, it could be any real number really. But what if the result is, yeah, it could be any real number. Oh, okay. It's greater than minus 2. Y belongs to R. What is the range? Oh, the range. Oh boy, the range. Why did I consider the domain then? The question asks about the range, not the domain. It can only be 0 or positive. then square root of x minus 2 must be greater than or equal to negative 2. Yeah, you can't have square root of negatives. So what did it say? Yeah, so when this is 0, square root of 0, basically have negative 2. Then that value decreases every time. Okay, moving on. What is the domain? So this is not a range, this is the domain for the function gx ln x minus 3. I'm not sure what line should be greater than 0, I guess. Because, no, it should be greater than 3 because line of 0, I'm not sure what's that. Line of 0. So, line of 0. What is this? Bad connection. Reload. Log of 0 is undefined. Okay, so in this case it has to be greater than 3. Logarithms are undefined for 0 or negative values. Yeah, I should note this. Okay. Next question. What is the range for the function x squared minus in the range? It's not the domain, the range. So x cubic minus 8. So the range could be the real no, the range. So assuming this is the starting point at 0, so you have minus 8. Assuming this is negative 1, negative 1, negative 1 minus. What if you take in negative 1 to the square root of x? Negative 1 to the square root of x. Right, so that's it. So x to the power of 3. So if it's x to the power of 3, x to the power of 3, what is the range? Now, if you're assuming, I think it's the r, because if you have minus 1 to the power of 3, you basically have minus 1 minus 8, and that's minus 9. And it's not really an option here. X greater or equal to negative 8. You could go like negative 10. So go for R. Can take any value within the set of real numbers. So x minus 8 can also take any value within the set of real numbers. Therefore, the range of g is R. Yeah, so if our assumption is correct. So in the case you can take any number, and then you will end up. So if you take minus 8, you could also take minus 10. There's no harm in that. Okay, what is the domain for the function of x square root of x plus 3? So as long as x does not equal minus 3, we're good. Greater than or equal minus 3. No, it has to be greater than
because if it's minus 3, then what is the domain? So it has to be anything other than 3. So this does not work, because if you take 3, negative 3, you will end up with 0. B greater or equal minus 3. You can't really take this option, given it's the negative 3. Negative 3 plus 3 is basically 0. And x greater than 3, greater or equal than 3. Yeah, this could work. But this doesn't work. I think this is the closest one. Why? Okay. A square root is undefined for negative values. What about the 0? So x plus 3. Okay, so the square root of 0. Is it possible? Oh my god, that was a silly mistake. So square root is not for negative numbers only. It has nothing to do with the 0. Square root of 0 undefined. It's going to be 0. Okay. I always thought it was undefined. That's why I can't. Square root of 0 is 0. Square root of less than 0 undefined. Negative numbers only, not 0. Okay, let's keep going. Here. Here. Next question. What is the range for the function g of x? That's the range, a to the power of x. So if it's 0, it's 1. That's 3. Honestly, it could be any number. Whatever the value is. I think it should be greater than... So what is a to the power of... What if we go a to the power of negative 1, or negative 2? What if it is like negative 27? So there's this always value that you will always get. So it's always greater than it's asking the range, not the domain. So the range is always greater or equal than 2. Is it D? Oh. Because if it's e to the power of 0, you get 1, right? Yeah, and 1 plus 2 is actually 3, so it's always greater than 2. Oh, silly mistakes, whatever. What is the domain for the function? I was asking for the domain. X minus 2, x minus 4, x minus 1, x minus 3. This shouldn't be 0. That's the rule. So this shouldn't be 0. 0 minus 1 doesn't matter. So 1 minus 1, that's 0, and 3 minus 3, that's 0. So you'll end up with 0. So as long as this doesn't equal 1 or 3, x does not equal 1 or 3, good. Because results I got like 3 wrong. Alright, so I passed with this. I'm through with this, right? So we're moving on to this. I think we should keep a link to these for the domain and codomain functions. I think it's important to Just quickly revisit them later on. So source, we could go like source, then you could have it here. Just in case you don't have to like constantly keep the tabs open. Alright, the set of exercises for the composite functions. Alright, so f of x, 3x minus 1, gx is equal to, and what is, so g of x is first x squared applied to this, so 3x squared minus 1. So 3x squared, where is it? 3x squared minus 1. Next question. If you have f, so first of all apply this to x squared, so all squared. This is the closest one. Next, I think I have to solve the functions now to be able to answer all of these. So 2 to the power of x. So gx first, the power of x, and then apply it to f. So 2 multiplied by 2 to the power of, no, you have g of x, that's like 2x, g of x. And then you apply to x to it. G of x applied to x is 2 to the power of x. It's tricky or what? So 2x, that's like 2x, right? Alright, so g of x applied to f of x. So in this case, this is 2 to the power of x. It should be 4 to the power of x, right? What's really going on? I'm a bit confused here, man. What the hell? 2 to the power of x, that's normal. Got it. You apply this to here. 2 multiplied by 2 to the power of x. G of x applied to f of x. If it was the other way around, then we would apply 2 to the power of 2 of x. I think x plus 1. Gx is 2 to the power of x. Okay, so f to the power of x. Yeah, so oh, yeah. What the hell? When you have the exponent, if it's empty, you add 1. It's basically, this means 1. What a silly mistake. I should have pressed my calculus bit. If f of x equals to x, it's a bit like ages since I've done mathematics, man. It's so embarrassing. Whatever. We're learning, right? Yeah. So if f of x equals 2 of x, and so it's the same equation flipped. So this should be rather easy because you start off with f of x to the power of x, and then you apply. So it's 4, so it's 2 multiplied by 2 to the power of x. No, it's 2 to the power of 2x. Yep. Now, this is a fraction. For x does not equal 0, then what is f by f? So this multiplied by this twice. Not multiplied by twice, but so 1 over x. So 1 over x. Yeah, 1 over x. So it's like, as long as x does not equal 0, then you end up with like 1 over x, and then you would have to go like 1 over x. So if you go like to equal x, 1 would cancel the 1 and you'll end up with x. So if f of x equals x squared plus 3 and g of x equals square root of x minus 3, what is the domain? Now we're talking about the domain, not the range. Of f composition, g composition with f. In this case, we're starting off with gx, so the gx has to be all the numbers but not negatives. So anything that doesn't equal, so it has to be greater. So the domain is greater or equal 3. Yeah, greater or equal 3. And then you would inherently apply that to x squared plus 3, the end result, yeah. So x minus 3 plus 3 equals x. Because you basically apply the composition. Now, x would normally have the domain of all real numbers. But because it's a composed function, you must also consider g of x. So what we've done. The domain for g of x is all the positive numbers greater or equal than 3. That's the only thing you could eliminate the negatives on the square root. F and g are both defined on the set of real numbers. Okay, both real numbers, fine. What is the value of x? For what value of x does the composition is interchangeable? So what value of x? I think we need to use the paper now. So I have a paper now, so I think you could follow along and try to solve this on your own. So g of x is like x plus 2 applied squared. That's the first g of x applied to f of x. And for the second case, you take on x squared and you apply it. So x squared plus 2. And that's what you so in this case, what value would in this case we just apply the options given to us. So clearly the 0 doesn't work. For the 0, the first one would equal 4, 2 doesn't work. So b is eliminated. Now half, if you apply the half plus 2 out of the, I think we should be looking at, so half squared, this equals 3. So half plus 2 all squared. Now half plus 2, 1, 2, 1 over 2 plus 4 over 2, which would equal 5 squared, 4, which would equal 5 over 2. Interesting. That doesn't work. Let's use the calculator. It might be embarrassing to use a calculator, but let's assume we have a calculator with us. So 1 over 2. Oops. So that's 0.25. Now if you have that squared, 0.25, then you have 2. That's 2.25. This would equal 2.25 for the half. But if you have half plus 2 squared plus 2, that's like 2.5. That's squared. 2.5 squared. 6.25. 2 plus 6.25. It's not the same, so the half doesn't really work. What if this was negative half? 1.5, 1.5, Okay, we're getting somewhere here. Squared x equals 1.5 squared. 1.5 squared. Okay. It's 2.25. No, this would equal 2.25. I think, yeah. So it's negative that works. It's negative half. Okay, so the composite function, you would end up with, oh, it would have been easier to solve for x instead of us trying the different values applied to both. Okay, what's silly of us to do? Bye. Now, so if you're assuming that f of x equals g of x, and then we know this is the end result of f of composition of f and g and composition of g and f. So if they're both equal, then we will solve for negative half. F and g are both defined on the set of real numbers, and c is a constant. For all values of x, what's the value of c? Okay, so we could use it the same way. Yeah, we could apply it the same way. We could do the composition for both. So I'm going to solve this on paper as well. So g of x applied to f of x, so that's cx plus 5. G is cx plus 5. Now we're saying that set of real numbers, so we could use any number. And to make things simple, to simplify things, we're just going to use 1 in the final implementation. So c of x applied to f of x. So we know that f of x is cx minus 3. So if we apply this to the equation, we will have, so it's c multiplied by cx minus 3 plus 5. So we will end up having this function, and then the other function would be, so if we apply cx plus 5, this is applied to c minus 3. Isn't that correct? Yeah. That is right. So we can opt for 1 here. So it could go c squared. This is 1. Plus 5 is equal to square so we take this from here, that's not c squared minus 3c minus 3c plus 8 is equal to c squared plus 5c, and then if we make this one there, if we move this one to the other side, so we can get having, so and then we should remove, so we move to the other side, we eliminate the c squares, and then divide 8 by 8, and you have c equals 1. Yeah, so you basically assumed that you could, because you have all the real numbers, so you could just substitute, so c squared x, and then you treat the c as the variable you're solving for, so you'll end up having these two equations, c squared of x minus, and then you just substitute for any random value for x, and then solve accordingly. Alright, so if f of x equals x plus 2, and g of x is 1 over x minus 2, what is the domain for the composition? So we start off with f of x. So f of x, then you apply this here. So it would be 1 over, so when you have like 1 over x plus 2 minus 2, so 1 over x. So x has to be greater than 0. It shouldn't be equal 0. You could have anything else. Yeah, 1 over x, and you could have anything else. Nice. Remember that we're applying gx first. Now that although g is undefined when x equals 2, for the composition, okay, so shouldn't equal 2. So if it's 2, 1 minus 0, 1 over 0, gx is undefined. Yeah, now that although g is undefined when x equals 2, is defined and equals 1 over 2 squared because it's a composition, so okay. So x squared, f of x is s cubic, and g of x is 1 over x plus 1. The domain for f, okay, the first one, the real set of real numbers, and the domain for g, x belongs to n while x does not equal to 0. Fair enough. For what value of x does f composition of, yeah, we'll have to solve for the equation again, similar to what we've done earlier. So let's do that. I have a paper with me, so you could just simply do the same. So g of x, so g of x is 1. So apply that 1 over x plus 1 cubic. And then for the other one, f of x, that's like 1 over x cubic plus 3. Right. So now, when you solve for both, now you need to decompose the cubic part here. So it's like you applied it thrice. So you need to decompose this. So the decomposition, if I'm not mistaken, it's like you multiplied it 3 times. Plus 1, 1 over x, plus 1, 1 over x, plus 1. So there's a function to decompose. Let me look for it. 1 second. Now I'm not sure if this is what we should be dealing with, but let's just opt for it. So A, B, C, D. 1 second. So basically this is what we're looking for. Polynomial function. So you have, so in our case it's like 1 over x plus 1. So that's like 1 over x cube minus 3 1 over x squared plus 3 1 over x and then minus 1, and then for the other end you will have 1 over x plus 1. So in this case you'll have 1 over x cubic minus 3 1 over x 3 1 over x squared plus 3 1 over x minus 1. So these would eliminate each other, so you will end up with negative here, so that would equal to 1. If we move this to the other, so that's like 3 over x squared plus 3 over x equals 2. And then so you would end up solving like 3 over x squared plus 3x out of x squared, which equals 2. And then you will end up having 6x out of x squared equals 2.
eliminate 1, so you will end up with 6 over x equals 2, and then you will have 2x equals 6, and then x would equal 3.
That should be it.
I think I've missed the limitation somewhere. Yeah, it's actually negative 3. Oops, it's not right. I've missed something here. I've missed the negative here. I've missed the negative. So negative 3. Man, that's a silly mistake. Negative 3 is not 0. Of course, that's not right. It's a mistake. I've done something wrong. Let me try to resolve it again without looking at the answer. So let me try to solve for it. I've missed the negative sign somewhere. Let me just retrace my steps. I'll just pause the video here and solve it on my own time. So yeah, I've done. So I had a mistake on the decomposition of the expansion of the function here, of both of these functions. So let's look at the answer. So the answer is actually -1. Yeah. So we've done this right. So the decomposition is actually 3 to the power of 1 over 6 squared and so on. So, and then you eliminate the ones here, you get rid of the ones, and then you also get rid of the x3. One eliminates the other. You'll be left with 3x over x squared plus 3 over x equals 0. If you get rid of the x squared, you will end up with 3 plus 3x, because x squared out of x is actually 3x. And that's it. And that's so this is the quiz results. So we've done not so bad actually. So we've had like an 80% success. Nice. So for the decomposition, we should have this kept in the records. That's just the decomposition, and then we could go like source would equal. There we are. Nicely done. Let's see what else we've got. So we've done this. Let's go to the so we solved this, didn't we? But apparently this is a different. So if f of x, so this is about functions and mappings. Yeah. Remember, let's finish this. So f of x is 4 over x, and g of x is the square root of the power of 3x minus 1. As g, composition of f of x. I like that they have complicated matters for us, but no worries. So f of x applied to, so this would equal, what is g, the composition of f and g of the power of x. So you would have f of x first, so for 4 over x minus 1. Next question. Which of the following is not a function? So definitely this is not a function. And those are different values for x. Certain that this is not the right answer. This is not the right function. Simply because you have two different crossings. One value. Nice, we've got it all right. So for the functions and mappings, we could just opt for this as a resource. Source, we could go domain and range and functions. Like here. So nice. I think we've covered a pretty good chunk. So the next So the next topic would be, so we've known the images is basically the range. An image is the range, and the next topic seems to be surjective, bijective, and stuff like that, the weird notations here, which we will be reading about next. Injective, surjective, bijective tells us about how a function behaves, matching the members of set A to set B. Okay. This is not a function because the single value of A points to multiple values in B. We know that. Now, this is a function. All elements map to a value. Now, this is injective. This is surjective. B can't have many A. B can have many A. Okay. B can have many B is surjective, not injective. Bijective, injective, and surjective together. Okay. So all elements of A point to an element of B. It's like everything points perfectly without having like the same number of elements in A point to the same number of elements in B, and both have the same order, the same cardinality. Surjective and injective. Injective you can have, so 1A was exactly 1B, that's also bijective. Every injective is a bijective. Okay? Every surjective is a bijective. Is that it? No, not really. I don't think it is. Because you have more number of elements in. So every bijective is injective or surjective, that's it, yeah. Okay, so I think we just need to dive in this more on the next video. So, until then, have a good one. Cheers.